Good morning. I'm glad to see everybody here, especially with the mouthful of a title that we've put together for this talk. My name is Andrew Hart. I work at the NASA Jet Propulsion Laboratory in Pasadena, California. And I'm going to be talking to you today about a software package that we have put together that we've called Object-Oriented Data Technology. It's previously been developed only at JPL, but recently released into open source. And we're very excited about that. So I'm going to start off just briefly touching on some of the challenges that we have encountered in building systems for large-scale research in different domains, not just the health domain, but certainly including applications. And then I'm going to talk a little bit about what ODT is and how it helps with the process of building these systems. Just to make that concrete, I'll go through just a couple of applications of ODT that include work that we've done for NASA and work that we've done for the National Cancer Institute, and most recently work that we've done with some of my collaborators who are here from the Children's Hospital of Los Angeles. And I'll just close by talking about ODT as open source and where we want it to go, where we're looking for contributions, and how to get in touch. And this is probably going to take 30 minutes, after which there's going to be a little panel session. My two colleagues will come on up here to the thing and we can answer questions. If there's any questions after we run out of time for the session, I'm more than happy to stick around and answer. So, if we look at healthcare research, research in general, but particularly some of the healthcare research, that it's becoming increasingly collaborative. And with that comes sort of an inherent increasing distribution of geographically of the participants. And a number of things are driving this, including some of the scale, the complexity, and the cost of what's trying to be accomplished. And it's driving cooperation outside of organizational boundaries. And even if that weren't the driver, there are some opportunities for scientific discovery that just make themselves present once your data sets grow. And so one of the easier ways to make your data grow is collaboration and cooperation. But hand in hand with that has come the need for technological support to make sure that as you grow beyond the bounds of a single institution, you don't lose efficiency, to make sure that you can carry out this research in a distributed virtual way, the same way, or approximating the way that you could do it locally. So the software I alluded to earlier is called Object-Oriented Data Technology, and really what is it? In simplest terms, and some of these aren't simple, it's a data grid software infrastructure for constructing large-scale distributed data-intensive systems. And so what it is really is it's a reference architecture, and that means it's a way to build, it's one way to build these types of systems. But it's also a product line, and that means that there's real software components behind this, which you can, they're built to be reusable components that you can pick and choose to fit your particular usage patterns. And they're built using common design patterns that should be familiar to software developers, so that they are easy to integrate and also easy to extend. But at its most basic, it is a middleware layer that helps connect clients with data. So ODT was funded out of NASA's Office of Space Science in 1998, and it was funded to address these critical shortcomings with the way that science data systems were being built for NASA missions. Since then, it has been applied in a number of different scientific domains, some of which you see listed here. Most recently work with Children's Hospital of Los Angeles in constructing a network for the sharing of pediatric intensive care data. And in 2003, it was awarded the NASA Software of the Year, or runner-up for NASA Software of the Year. The ODT itself is built on a couple of principles. I've outlined them here. A distributed system can't afford to be a vertical stack, so we really rely on the division of labor and the configurable nature of these components. Technology independence has also been important, especially for a middleware layer. You want to make sure that whatever you're building there to connect clients to data doesn't depend on what those data repositories are using as their ultimate implementation technology. And then of recurring importance is treating metadata as a first-class citizen. A lot of data architectures are focused on, well, what's, the data. But especially as you grow and scale, descriptions of those data come in very handy, especially for doing things like discovery, search. And then separation of software and data models. Your software and your model may evolve along different paths, and having a decoupling between them allows you to react a little bit more flexibly, such that a change in your model doesn't necessitate a complete rewrite of your software. And finally, as the slide previous alluded to, the modular and domain agnostic nature of the ODT package itself, it means that you can use this for the purpose of building distributed scientific research environments, regardless of what type of data you're really pushing through those environments. So just touch on this briefly. Some of the core framework services, what does this middleware layer provide? And I talked about connecting clients to data. There are several services, basically canonical services. There's an archive service for storing data and metadata, a profile service for discovering metadata. Metadata, just to be absolutely clear, is data about data. It is data that describes your data. If you take a digital photograph, the make, model, time, resolution of that photograph is metadata about that photograph. And metadata about your research data is oftentimes extremely important. And so profile service helps to deliver that from the underlying store. The product service actually delivers the real bits of whatever it is that you're looking for. A query service helps to manage sets of these profile servers and product servers, because ultimately we're going to be building a distributed network in which there are multiple instances of all of these things, and you're going to want to be able to query them in a distributed fashion, because it is in many cases infeasible to move all of the data into one location. And finally, a data grid service that is provided by the framework helps to provide the interfaces and utilities for creating mechanisms to access all of this across the web. So this is the first of three sort of applications I'll touch on. This is the only one that's not specifically health-related, so I'll just go through it quickly. But it's important because it was the first successful implementation of the ODT framework. The Planetary data system is NASA's official archive for all of its planetary data, and this is spanning missions over the last 40 years. They're located at 9 nodes spread across the United States. And each NASA mission has the requirement that their data must be added to this archive, so it's continuously growing. However, prior to October 2002, there was just simply no way to perform a global query and discover what data was stored at each one of these nodes. Primarily offline, talking to somebody, getting your data via CD-ROM. And there are some unique challenges to the PDS that made sort of building a traditional data system difficult. One is that NASA flies unique, one-of-a-kind missions. You can't really abstract any. There are a limit to what you can build in a static infrastructure because the nodes are changing, the models are changing, and the data that gets captured because of the diversity of the missions is quite different. As a result. Or rather, in addition, there is this requirement that the data collected by NASA belongs to everybody. It's the public's data, and so you have to be able to share the science results with the community at large, including the research community. So basically, the architecture that arose to address this was one in which you have a distributed data system environment with federated governments. Each one of those nodes maintains local control of the data that it manages because it absolutely needs to perform its own local research while making it available to the broader community. Of critical importance, and this is a recurring theme in each of the three applications here, is the development of a common information model, the domain information model, treating your data architecture as important as your physical architecture. So we used some of these concepts that I was talking about earlier, ODT query handlers, to provide an interface to these distributed services, and some of the product and profile services to provide data delivery and archiving and storage. And then there is a public access point to the PDS, which was on the screenshot 2 slides ago, where all of these distributed systems have to publish some of the information, information about what they contain to this public portal so that it can be searched. The last thing I'll say about PDS is just that this is a large slide about the general architecture, but the highlighted bit there, the data architecture, is what I think is very important, is when designing a big system, considering the structure and nature of your data is one of the first things that you need to do if you are ultimately interested in scaling beyond your boundaries into people that may not be familiar with it, or maybe using the same type of data but have called it different things. Having a defined data architecture was one of the things that has made the PDS system a success, and it's not static. It continues to evolve. Okay, so now the second one is the second application that we've done with ODT is the Early Detection Research Network. This is a project out of the Division of Cancer Prevention, National Cancer Institute, and their focus is on discovery and validation of biomarkers for cancer. And it's been around since 2000, as this is just entering its third funding cycle. It consists of just over 40 research and educational centers around the country, and they are simultaneously performing studies in which they're either sharing data or sharing results. And the project has sort of distinguished itself through placing a strong emphasis on the role of informatics in supporting this distributed research. Just to give you a quick sense of maybe what is the EDRN composed of, there are biomarker development laboratories who characterize these biomarkers. There are reference laboratories that take care of some of the validation issues. The clinical epidemiology validation centers conduct the research, and then there's a data management and coordinating center that helps to do the statistical analysis and provide a lot of logistical support. They basically tie the network together from an organizational point. So at this point, there's still a break. How does NASA and the NCI get together? There was a talk given in 2000 at the National Academy of Sciences about some of the successes in the PDS, and someone from the NIH had been in the audience and had made the connection between the work that was done there and the work that was planning to be done for this EDRN network. The interagency agreement has resulted essentially in the formation of an informatics center for EDRN, and that is headed by my boss, Dan Crichton at JPL. So EDRN data, they collect, they generate, analyze, process, and store a lot of different data, including specimen inventories, which is basically information about the research specimens that are at each of the sites, studies and publications, biomarkers, and science data, which is essentially raw and also processed data from the actual instruments. All of this helps to generate a complete picture of the state of the art of research for a particular biomarker, which is very valuable to the validation folks in trying to determine whether or not this really is something that indicates cancer or cancer risk. Just going to touch on this quickly is that on the left-hand side of this diagram here is the local laboratory, and this is what a lot of current health IT software addresses, and with great reason. The emphasis that I'm going to be placing on is on the right-hand side, which is what happens when you want to connect many of these laboratory systems together. Different set of tools, different set of concerns, different set of challenges. One case study was something we called ERNI, which is the EDRN Resource Network Exchange. It's essentially a virtual specimen bank. There were maybe 12 centers that had specimens. They had their own systems for managing them. They were using them their own way. We wanted to combine that so that a researcher anywhere could get access to the specimen information stored at each of these locations. But everybody's using their own schema. Everybody's using their own processes. The only way to do this is through, we found, was through coming up with an accurate model of our domain that clearly and unambiguously described attributes of each of the things that we were interested in and performing distributed query. There was no way to move all of the information to a centralized database. So this is what it looks like from an architectural point of view. And what I really focus on here is the right-hand side. You've got all of these specimen databases, and for the purposes of ERNI, they are distributed physically around the country. And in front of them, these green boxes, we've placed ODT product servers at each of the sites. So it's a little thin layer of software that runs at each of the individual sites. On the left-hand side is the main infrastructure for Ernie for the querying and the search and some caching. But what you would be able to do as an end user is to make a single query that is expressed in the language of the domain model, which gets sent out to all of these sites, and the product server sitting in front of the site's repositories carries out the translation between the global model and the specific implementation, such that the relevant data actually does get returned. One of the nice things about building this or using ODT is that the modular nature makes it fairly easy to extend, customize, and therefore connect research that's going on in other areas. EDRN is not the only organization interested in this type of research, and we've been able to connect in a number of concrete ways to, for example, the Cancer Biomedical Informatics Grid has a CA tissue suite, which also does specimen information tracking. And we have connected the EDRN grid with the CA Big grid through an Ernie CA tissue wrapper. Also, the Canary Foundation is doing similar research, and they use software from a company called Genealogics, which makes heavy use of Amazon's S3 cloud storage system, and we have been able to plug in to that to be able to share data from EDRN researchers with Canary researchers. The end result being that you're getting data from all of these different places, and physical location becomes less of an issue. And you can the goal for EDRN is to build a semantic grid for this that can translate into a bit of a knowledge environment where a researcher can quickly understand the state of research for his or her biomarker, as well as contribute to furthering the state of the art. A couple lessons that we were able to take away from this is that having a vision and an architecture that supports that from the beginning is very important, more so than individual decisions about what technology will be used to implement that. And that also at the same time that science support, getting support from the scientists and the researchers themselves and maintaining those relationships throughout the process is absolutely critical. Along that line, incremental deployment so that you can give the scientists and researchers something that they can say, this is what I want, this is not what I want, and being able to do so quickly and repeatedly also helps maintain these relationships. IRB processes for us, just something we couldn't get around. You have to build for that. And then also just the fact that building a distributed architecture is a bit of a challenge for individual sites that are perhaps more used to simply dealing with their own environment and the control and the and everything that comes with that. So there is an educational process on both sides where we at JPL with perhaps less clinical experience learn a little bit about what the challenges are on their end and vice versa. So the third application here that I just want to talk about is the one, and this is my colleague's work here. This is the VPICU. So what is a VPICU? A VPICU is a virtual pediatric intensive care unit. And it's a collaboration between about 85 multidisciplinary pediatric intensive care units spread out across the United States. And they have a number of high-level goals, essentially just to improve patient care, educate practitioners, conduct research, and reduce the cost of providing care. So the data here with VPICU is quite different from the data we were using in EDRN. This is secondary use of observational data. This is EHR monitor annotations. And in many ways, this data differs significantly from what you might call an ideal research set. I've tried to list them out here, but essentially it's continuously growing. The formats are wide and not always, they're sometimes proprietary, not always open. The data itself may be fragmented across different stores, and it may itself be incomplete or even worse, inconsistent, and it comes with a bevy of legal restrictions on its use. So there's a number of sort of challenges that are unique, not to VPICU so much as to clinical research data. So the goal, in simplest terms, is to be able to get data from all of these different sources, align it with a model, transform and process it to extract some knowledge, use that knowledge to drive decision support in the pediatric intensive care unit, and also at the same time improve the value of that data by distributing it and collaborating with others that are trying to do the same thing. And so it's that last little bit there, the data sharing over a national network, which really was what brought JPL into the picture because of and this is the place where ODT can really make a difference. Again, so the principles, the basic principles are we really want to decouple from vendor databases as soon as possible because we don't own them, we don't have access to them. We want to, at the same time, be able to take data from many different sources and align it against the same model. We're also interested in, we know this is a long-term project, and we're building a system to answer questions we haven't thought yet to ask. So you can't really, you need to be able to have the flexibility to generate and regenerate and regenerate and re-optimize and reorient whatever you need to do. And then, again, we're not building this in isolation. We want to be able to provide multifaceted access, whether that be through API bindings for various languages, R, Python, or web access from other PICU centers that are interested in sharing and extracting data. So there have been some common threads across the three examples I've given, and you come up with an algorithm almost, if you will, or a recipe for creating one of these distributed data systems. The one we've got for vPICU here is basically start with your information model, understand what it is that you're trying to extract, what it is that is going to feed your research, what's going to feed your analysis, what's going to feed all of the work that you intend to do downstream, and then work on developing the compute resources to perform that extraction, that alignment, that transformation, the loading, the construction of your research databases, and the ability to communicate that information to partners and collaborators across the web. So this is another architectural picture, what we came up with for vPICU, and I will just go through it very quickly, step by step. On the far left there, you've got the original data sources, and these are things like the hospital's electronic health record, homegrown applications, clinical applications, and actual monitor data. These are raw data sources that are almost certainly going to be in different formats, have different levels of availability, and in the case of, for example, the hospital EHR, not something that we have unfettered access to, that we can afford to be messing up, certainly, or even accessing at all times. So one of the first steps is within CHLA to take all of identify the data sources and extract them into a new common aligned data source. And essentially the value behind this is that if you've got patients represented in many different systems that are speaking different languages, you can then take and reorient and get all of these things so that you've got a complete stream of information for an individual rather than a number of fragmented streams. So that's the data at this stage of the architecture has been normalized, and it's stored in a suitable format that you can then take it and ingest it into these research databases. So the research databases, using some of the ODT services I mentioned earlier, are application specific. They're essentially designed, you can build as many of them as you want because you've got all the raw data, and you basically build what suits your query. So what questions are you trying to answer will dictate how you structure your research database. Let me just make that clear, is that the research database doesn't have to be relational. It doesn't even have to be a database. The key is it is an organization of your data so that it is suited to answer a particular question that you have. And these are just a couple of examples of possible research databases. The right-hand side of the diagram with the cloud there is the fact that this is everything on the left within the dotted line there is belongs to CHLA. So when I was going through that extraction bit, you might say, well, I thought you said we're not moving data to one location. We're not making copies of all of this, and that's very true. Once you start connecting let me clarify that the data system, the file system, data system in the middle there is really, you haven't copied things. You've simply put them in a location that is, and transformed them into a format that is a little bit more amenable to building these research databases. What you have not done is taken data from many different sites and made one gigantic mountain. That is not tenable, frankly, for a lot of the different reasons, including privacy considerations. So on the right-hand side, we've got data analysis tools. You've got a web interface for searching and discovering what data has been collected from the PICUs, and then a network mechanism to connect this exact picture and replicate it across, ideally and eventually, all of the 85 participants. So I'm just going to go back to that algorithm I said, and I've highlighted in green the areas of that algorithm in which the software that we're discussing today, ODT, plays a role or can actually be helpful. And just from looking at this, the middleware nature of ODT becomes almost visibly obvious here. You have to demonstrate, you have to be able to develop the model. You have to know what data you're going to be dealing with. But once you do, it becomes a matter of encoding that into some of the configurable software and allowing the query handlers, the services, to basically provide you with a way to bootstrap your way up to a big system without having to do the development work from the ground up. And then on the other side, when the data comes out, it's again on you to develop research tools to analyze and handle the data mining that you'd like to get value out of your data from. So that's a bit of a whirlwind tour through a couple of different applications that we have gone through. ODT was, up until this year, developed entirely internally to JPL. It's been released to the Apache Software Foundation and is incubating at the moment, which is their term for software that is on its way to becoming a top-level Apache project. This is a bit of a landmark in the sense that it's the first NASA software licensed this way. This is something that we're very happy about because we hope it means that a larger community will be able to help us participate, tell us, and really grow this software as a tool so that less and less people are finding the need to start from the scratch, or even worse, being put off by the difficulty of building these distributed research environments. So if you'd like to learn more, we have a website at the incubator. There's a mailing list. Anyone can join, lurk, participate, whatever. We are also on IRC, and there's a whole bunch of friendly people. So we'd be more than happy to talk about anything related to ODT or specific domain implementations. So I just have a couple people I'd like to acknowledge, but thank you very much for coming and taking a listen. Dan Crichton at JPL in particular, the PI for informatics for EDRN, also the manager of the engineering node of the Planetary data system, and Dr. Chris Mattman, a senior computer scientist at JPL. He would be giving this talk today in my stead if he was not at another conference. He is probably single-handedly the person most responsible for getting ODT into the ASF, and so we're very, very grateful and very excited about the potential. That's all that I have for the talk. I think at this point I've got two colleagues here. David Kale is a researcher at Children's Hospital Los Angeles. He has a background in computer science. And Robbie Kimani is a pediatric intensivist, also at Children's Hospital. And we are basically here to answer as best we can any of the questions that you may have.
Just switch on the microphone there.
Great. Sure.
When you're developing a domain ontology, how do you avoid introducing unnecessary bureaucracy or over-organization into your domain?
So the question about domain ontologies and not introducing too much bureaucracy into the process. That is a major challenge, especially and it grows with the size of your network, obviously. There's almost two sides of that, right? One is there's too much bureaucracy, and the other is that there's not enough participation. On EDRN, we had experienced both. We basically there was a bit of a carrot in the sense that some of the participation was mandated by the funding process. All of these people were brought together. But I think, how do you avoid the bureaucracy? I think I mean, it's $1 million question. It is almost inevitable. But I think that breaking yourself down into increments and not getting too tied up in the ontology or as its own thing without a practical application is one step, in the sense that design something, understand that it's an iteration, work with it, make something, understand the weaknesses, do it again. That somehow tying it to something practical helps, you avoid some of the discussions that tend to get people down in the weeds. Sure.
Follow up on that. I think OpenEMR builds archetypes of their models, and then has the community evaluate those and put them into the system. Have you guys thought about using that type of strategy in the ontology project?
Right. Well, so that's a great idea, because I mean, if you're surrounded by people that think just like you, you're not going to maybe see some of the things that the community would say, well, you've totally missed this. That's excellent. I think what we've done, at least in the EDRN side, is we have encouraged. We have a much smaller community. It's just these at the moment these 40 research organizations. So it hasn't been. We haven't experienced the sort of high-level bureaucracy where we're trying to solve everybody's problem. We're solving a very narrow problem, and so that has helped dramatically. But no, I don't think we've released our. We've released our ontology to the people that are participating, but we haven't solicited feedback from people outside of the network. Sure.
I'd like to ask about data, from the clinician side, what's the value of having access to this type of data from an open perspective, both from an open source side and just as a research?
Yeah, one of the big challenges with medical data, particularly data that we've had at Children's, is we've had an electronic healthcare system in place for 6 or 7 years and have had access to that data for quite a bit of time. But being able to tie that data together to actually answer any meaningful research question has been really, really challenging, because finding a way, they're stored physically in different locations, different people have different access to those sorts of things, and it just makes it really hard to put together any sort of comprehensive research question. You can do very specific things where you get data from one database or from one data source. So having a system like this that ties that all together has been invaluable. Yeah.
Sure.
Have you got any sort ILM policy?
No, I'm sorry, I couldn't quite hear you.
Have you got any sort of ILM policy, information lifecycle management?
ILM policy.
You're not ILM?
Sure.
Yeah, I'm not. Could you be just a little more specific?
Yes.
Sure.
Okay, so in the archive system, there are like policies to move data between tiers, or like to get to take new data and put it into different storage systems. Do you have any support for that?
Sure. Okay, right. There are. Let me see how I can bring this. Some of the ODT components, the catalog and archive service, absolutely. There is support for what we've called versioning, which is essentially if you're going to be ingesting something and potentially updating it in the future. This traces some of its heritage back to the NASA origins, in that you can never delete anything, and you change something, it supersedes but doesn't replace. So there is a system in there for making sure that that we support data as perhaps it changes. Sure.
Are these experiments set up like as with web service workflows? Like, is that like the vision of this, or it almost seemed to me like you had a single interface where I just come in and say, well, this is the experiment I want, or whatever, and then that goes and talks about a component. But the other things that seem like a Taverna, where you go with one service, get the data, go to another service, do an analysis.
Right. So the question had to do with, is there a single interface here to this, or is there support for multiple?
Yeah, I think that's like how C8 Grid is set up.
You're right. Okay, so perhaps the slide's oversimplified. There is nothing in the system that inherently says, here is your one access point. If you're referencing the architecture slide where there was a cloud and the web portal, that is essentially, sometimes it's nice to have a single point of entry for the purposes of discovering what data is in your system. But there's nothing in the system that restricts you to having that single spot.
So people are like publishing research papers. How are they approaching the architecture? Are they approaching it from that single point of view?
Sure. Okay, I see. So, for example, in the case of EDRN, there's a number of tools that we have developed to do what we've called data curation. Data comes in from each of these sites, and they have different levels of quality, or they're perhaps inconsistent, and that we're at one end interested in building a comprehensive, self-consistent repository of research information. So there's a level of quality assurance that has to go into that, and we've got a system through some work with Dartmouth University to provide a human in the loop in that sense, to basically say, look, I've gotten data from here, this looks correct or this is not, and they work as a liaison with the individual participating researchers to make sure that the data that we ultimately get represents the full picture.
Yeah. So are proprietary ontologies a barrier? From the clinical side, CPTs, things like that, gathering. How do you handle it? Having that stuff within your system, you have to license it.
That's an interesting question. I think that's something we're still. I mean, the VPICU.
Sure. So the question had to do with ontologies and whether or not proprietary ontologies are a stumbling block, and whether the plethora of ontologies is perhaps something that restricts or impedes progress.
Yeah, especially in medicine, and I think it's important to point out that the VPICU collaboration with JPL is ongoing and sort of in early stages. So we're actively developing our ontology for critical care data right now, specifically pediatric critical care data. And a lot of the questions we get from people is, well, have you looked at SNOMED? Have you looked at ICD-9? Have you looked at whatever? And we have looked at those, and we do think it's part of what we're going to do with our ontology, I think, is we're going to make sure that our ontology maps onto some of these other descriptions and ontologies. But none of those serves the specific I think what Andrew made clear in his presentation is you want your ontology to not be a giant catch-all. You want it to be focused on the research questions you're interested in addressing and to cover the data you're really interested in researching. And so what we really want to make a pediatric critical care ontology that's facilitates doing research, not just retrospective studies, but new kinds of research down the road. And so a lot of the sort of proprietary things are useful, and we certainly look at them for guidance, but there's no ontology out there that does what we want it to do, so that we have to sort of construct our own. And are they barriers? I mean, they are and they aren't. SNOMED it's useful to look at, and there's a lot in there, and there's a lot of things you can learn from it. On the other hand, it's huge, and it's clearly designed with billing in mind, so there's a lot of stuff in there that we're not interested in.
Yeah.
Okay. Yes.
Right. Correct.
Well, and then to follow on to that, if you don't mind, so are there plans to actually construct the system to where it would be valuable internationally, where you're able to peer your repository with other repositories internationally?
I don't see why not.
Well, I mean, is that part of the plan?
I want to speak for VPICU.
It certainly could be part of the big picture vision. I think that the shorter term is certainly the national network, which has been established and been created for quite some time. But absolutely, this could grow to be compliant, or to integrate all international units and with different facets of pediatric critical care, for sure, and not limited to pediatric critical care.
Okay, we're just. I think we're already run out a little bit. So, thank you very much. I will be around after the session and for the rest of the day. So if there are questions, and I think my colleagues will be too, so we'd be happy to answer your questions. Thank you.